bandwidth and power consumptions. Different kinds of optimizations have been proposed and applied for VR rendering. Some methods try to render two images using one draw call. However, they do not reuse the shading result between views. Some methods try to project shading results from one view to another view, but this method often suffers from the holes caused by the shading incoherence. So in this paper, we want to design a new dedicated rendering pipeline for VR rendering. Such a pipeline should include following features. First, it is designed for mobile GPU and can perform the rendering of two views in single draw call. Second, and the most important thing is that the pipeline should reduce the computational cost in both shading bandwidth and the shading instructions. Our pipeline is motivated by the following observations. First is the gap of the mobile cache. For the efficiency of bandwidth, most of the mobile GPUs use tile-based rendering. That is, the image is divided into small regions, namely tiles. At each time, the mobile GPU loads data for one tile into on-chip cache and performs the rendering. So our pipeline should consider the per-cache I/O and avoid 2 times of the scheduling and the shading in VR rendering. Here shows our second motivations. It can be seen in the rendered image that many portions of the shading are very similar. Specifically, while we consider different components of the shading, specular is dependent with views, but the diffuse and shadow are independent with views. Furthermore, the shading frequency of different shading signals are highly dependent with the scene. Therefore, per pixel shading per view is not always necessary. This observation has motivated several previous works. Adaptive shading or multi-rate shading applications have been proposed. For example, in the regions that are far from reflection lobe, specular color changes very slowly, so it can be computed in much lower rate. Same happens for shadow umbra region. However, all proposed multi-rate applications are not designed for VR rendering. It is non-trivial to directly extend their work to VR rendering. We have to design a new framework to reuse shading across dual views. Based on this observation and motivations, we bring our adaptive multi-rate dual shading pipeline. Here's its overview. It mainly has two new designs. First, we try to exploit data locality through a Typehair-based rendering. Second, we use cache-based scheme to reuse shading results between dual views. In the following of this talk, I will first introduce the Typehair-based shading and then discuss the shading reuse in dual views. Finally, I will show some evaluation of our pipeline. Let me first talk about how we exploit data locality through a newly proposed Typehair structure. Let's start from the simple diagram of VR rendering in current tile-based shading. It includes several steps, such as triangle binning, scheduling, rasterization, and shading. Unfortunately, even though the data locality is maintained in tiles, all triangles must do these costly steps twice for now. To combine these two paths in one, we introduce the Typehair structure. As you can see, two type frames in two views naturally intersect a region in 3 space. We call such a region Typehair. All triangles inside the Typehair region are guaranteed to be mapped to these two tiles in pairs, so the locality is maintained. Therefore, in our pipeline, we perform all the scheduling and shadings in terms of Typehairs inside the tiles. This is a fundamental change to the existing rendering pipeline. To achieve Typehair shading, we need to store extra information. The right shows the triangle tile list used in tile-based shading. Technically, for each tile in each view, a triangle list stores the index of all triangles overlapping this tile. In our Typehair-based rendering, we add a new triangle Typehair list to store the triangles overlapping both tiles. The triangle Typehair is built upon the triangle tile list. In the triangle Typehair list, we store the index offsets of triangles in the triangle tile list. In this way, the necessary triangle data can be quickly fetched during rendering. Once you have triangles of Typehairs, the order of the Typehair scheduling is carefully designed to exploit potential data locality. Take this 2D figure as example. We use 2 methods to optimize the scheduling. First, the Typehair is scheduled by labeling orders, as shown in the figure. In this way, the shading coherence is preserved, and the triangles that overlap in neighboring Typehairs need not to be reloaded. Second, the disparity of the Typehair index reveals the relative depth of the Typehairs. So we choose to rasterize sequence 1 first, so sequence 2 will have a better chance to be optimized by early Z optimizations. Okay, once we could use Typehair as scheduling until unit to perform rasterization and shading, we could localize the I/O and reduce the bandwidth. Then our next problem is how to reuse shading between views. In brief, the core structure behind our stereo view shading reuse is a cache-based shading system. A cache reuse shader stage is designed to adaptively reuse the shading result. We adopt the previous multi-rate shading pipeline in our framework. First, a coarse shader is added before the pixel shader stage. The coarse shader is computed at a lower shading rate, such as only 4 shading on a 4x4 squared. When the low frequency shading signal is computed in the coarse shader stage, they are resampled to per pixel shaded color. Utilizing the coarse shader, we could not only reduce the shading cost, but also reuse shading across views. We add a small on-chip cache to store the coarse shaded result. Once the triangle is rasterized and wait to be shaded, we will query the shading cache for the coarse fragments. If the query fails, we will compute the coarse shaded shader and catch the coarse shaded result. If the query succeeds, the catched results are directly resampled to 5 pixels. In this way, we save the computation of 4 coarse fragments. To query a suitable shading result, we use a hash function h and 3 values q, n, v to generate a unique key for coarse fragments. The q is the coarse fragment's screen positions, the n is the size, and the v is the flag to identify which view is in query. Once a query for one view failed, we then query the coarse fragment for another view and use the new key to generate the key again. Whenever a shading query succeeds with a catched coarse fragment returned, we need to determine whether the queried coarse fragment should be reused or not. We decide to use a cheap cache reuse shader to do this job. User can write a simple code to control how to reuse. For example, triangle I and triangle J have different positions, but the general key can be the same. So we write a simple shader to check whether the difference of the position between query fragment and the catch fragment is small enough to reuse. So once the shading catch query succeeds, we will invoke a cheap cache reuse shader to check whether the query value could be reused or not. If it could be reused, we resample the catch shading result to per pixel shading results. Otherwise, we still need to compute the coarse shaders. We have described the 2 most important design choices of our pipeline. Now let's show some evaluation of the new pipeline. We use a software GPU simulator to simulate our pipeline. Some common GPU optimization methods are implemented in this simulator, such as backface curling or early Z optimizations. We collect the on-chip bandwidth and per pixel shading instructions during rendering. We use various configurations to test our pipeline. Due to the limited time, we only show some important results here. First, let's talk about the bandwidth. Our GPU simulator uses L1 cache system for different data. In left figure, we show the bandwidth of different data consumed by our simulator. As you can see, our Typehair structure well exploits the data locality, reduce much of the texture and the triangle data reload. However, here we only show results of the one thing at a 16 plus 16 tile configuration. More results can be found in our paper. Then let us focus on the shading rate. In our simulator, for each pixel, we record the total instructions computed at the pixel and visualize them. The castle scene is tessellated and has the largest triangle numbers and the smallest triangle in our test scenes. As you can see, the multi-rate method did not handle the small triangle very well. So about 60% of the original shading instructions are still need to be computed. But our method needs to compute less than 30% of them. Result of detailed analysis can be found in our paper. As for image quality, we use SSIM as a quality metric. The overall difference is quite small. There are some artifacts after reusing shading results, such as on the curved surface, but the difference is barely noticeable in the final rendered image. There are more results can be found in the paper. So we thank the reviews for the people who help us, and we also thank the following funds. A few takeaways. Typehair structure maintains the data locality in dual views, and it is beneficial to replace costly shader computations with cheap catchy result shader. In the right is a video demo of our pipeline. And any questions?
Thank you. Does anybody have any questions about this? Yep, can you step to the microphone, please? That would be great.
May I ask if you have made some synchronization problem in between these two images?
You mean synchronize?
Synchronize.
Okay, so for each type here, we do the rasterization of two views in parallel. So you can first rasterize one triangle for one view, then to another view. So, and the type here is processed parallelly per horizon row. So synchronize is not a problem here.
Okay, thank you for that. Are there any other questions? Yep, please.
You mentioned some GPU simulator that you're using for this work.
Yeah.
Can you tell me first of all, what is the name of this simulator?
So there are papers about software rasterization in GPU published by NVIDIA. So I can show you so we use their code. They have a GPU simulator about rasterization and the hierarchy optimization, such that they have implemented this.
Yeah, I'm curious, how much do your results depend on this specific simulator that you used?
Okay.
And if the transferring is exactly the same if you implement this on a normal GPU, this is my question.
I think there are still some gaps between the simulator and the actual GPU, because simulator we only simulate some of the normal caching or something like that. You cannot expect the real GPU can simulate all. A simulator can simulate all the GPU things. We couldn't afford to implement a system complicated like a real GPU.
Yeah, because they do, they do optimizations in the drivers in the GPUs. They do a lot of things for VR.
I think our contribution here is the main concept of the Typehair. So we have to, we only need to show that we have the Typehair, the data locality is maintained, is our main concern. So we do not simulate all the things.
Okay, thank you.
Great. Well, we're out of time, so let's thank the speaker again. That's great. Thank you very much. So do you want to come?